All right, so for chapter 33, we'll be doing 3 problems. We're going to do problem 33, 51, and also, let me see which one this is, 59, okay? So problem 33. So this is a polarization problem. So we have this diagram. We have 3 polarizers arranged in this way. And initially, unpolarized light is sent into the system. Our 3 polarizing sheets with polarizing directions. Theta 1 is 40, theta 2 here is 20, and theta 3 is 40 degrees. With the directions of the y-axis, what percentage of light's initial intensity is transmitted by the system? So to do this, we, so initially it is unpolarized. So let's say the unpolarized light, we can use this symbol to indicate that's unpolarized. And let's say, initial intensity, I just call that I naught, okay? And then when it passed through the first, polarizer, we know that intensity is dropped by half. So you don't have to do, you don't have to do any calculation. You can just directly set that I1, we call this intensity, that's I1, which is, 1/2 I naught, because intensity is dropped by half. In addition to that, the directions of the polarized lights after they pass through the first polarizer will be in the same directions as the polarizing axis. So it will be in this direction. Okay, so I'm just going to draw it like this. So this is a light that can be transmitted through the first polarizer. And when the first polarizer with this intensity, and when this polarized light passing through the second polarized, so let's draw it this way. So it will be in this direction. So light in this direction. And then the polarizing axis is this direction. So we know that by Malus law, we know that the I2, the intensity of I2 would be I1, and then cosine theta squared. And that theta refers to the angle between the between the polarizing axis, which is this one, and the light that's sent through the second polarizer, which is this one. Okay, and we know that this one is already making angle theta 1. All right, and then this is your theta 2, which is here, theta 2. So your theta in this case will be the sum of theta 1 and theta 2, because that's the angle between these 2 axes. One is the second polarizing axis, and this one is just the light that's being sent through that one. So theta 1 is 40 and theta 2 is 20. So we will have I1 and then times cosine 60 degrees, and then you square it. So so my I2, I will get an I2, which is 0.125 I naught. Okay, and then so the directions of this line will be again, in the same directions will be in the same directions as the second polarizing axis, which is this one. Okay, so so we can actually draw it like this. So this is your second, this is the one that's being sent through this third polarizer, and with the angle of this one, which is theta 2, and your polarizing axis of the third polarizer is this, which is making this angle with the y-axis, which is theta 3, which is 40. So again, the angle between these two are 40 plus the 20. So your I3, the intensity of I3 is equal to I2, okay, and then times cosine theta square, and that theta is the angle between the third polarizing axis and this light passing through the second polarizer. So that again is 60. So you have the I2 and then cosine 60, you square it, and I will get my I3, which has a numerical value of 0.03125 I naught. So this indicate that the ratio, because you want to find the percentage of the line of the initial line intensity, meaning that you do the I3 over I0, and you will get 0.03125. You can leave it like that. You can say that it's about like 3.125% of light, of initial light that will be transmitted through the third polarizer. Okay, so that's basically how you would do it. As you can see that initially unpolarized, then the intensity will drop by half after you pass through the first polarizer, and for the rest of the intensity, you will use the cosine square cosine theta square law to calculate the intensity, and the directions of a polarized light will be always in the same directions as the one that's being passed through. So, for example, for the first one, this is polarizing axis, so the light that survive will be in this direction, and for the second one, the polarizing axis is in this direction. So that will be the directions of light emerging from the second polarizer. And for the third one, it will be in the same directions of the third polarizing axis. That's how you determine the directions of the polarized lights. Okay, so that's problem 33. And the next one I want to do is problem 50. Problem 50. 51. Okay, so let me erase this first. All right, so 51, it says light is incident at an angle that is 40.1 degrees on the boundary between two transparent materials, some upwards, and then let me see, some of the other light travels down through the next 3 layers of transparent materials, while some of it reflects upwards and then escape into the air. N1 is 1.3, N2 is 1.4, N3 is 1.32, N4 is 1.45. What is the value of theta 5? That's here. And also, what is the angle theta 4? Theta 1 is given. Okay, so how do we do this problem? We know that when you have light that's passing through different layers, which made of different material, we know that light, some light will be reflected and some light will be refracted. Okay, so for reflected ray, theta 1 here is the same as that one, and for refracted ray, we will use the Snell's law. So the first thing we should write down is that we know that you have the N1 and then sine theta 1, and that must be equal to the N2 sine theta 2, right? So you will write down N2 and then this is the normal, so straight line, and then this is your theta 2. So you will go by you will use the Snell's law to calculate to set up equation, and so you seem that you have to calculate theta 2 and then apply Snell's law at this interface and apply Snell's law at this interface, but you will find that this angle theta 2 is equal to this angle, which is the angle of incidence at this interface. And then so this theta 3 is the angle of refraction, and that theta 3 here will be the same as this angle. And so you have the N3 sine theta 3 that's equal to N4 sine theta 4. So skipping the intermediate refraction, you'll find that your N1 sine theta 1 is actually just equal to N4 sine theta 4. Okay, because the angle refraction at this angle is actually equal to the angle of incidence at this interface, and so by propagating through the different layers, we can just set up that N1 sine theta 1 is equal to N4 sine theta 4. So your N1 is 1.3. And then your theta 1, so sine of theta 1 is 40.1. And that is equal to M4. Your M4 is 1.45. And then times the sine theta 4. So from there, you can actually calculate theta 4. So I got my theta 4, which has a numerical value of 35 35.27 degrees. Okay, so this is how you calculate by applying Snell's law, even though it looks like you have to calculate theta 2 and then theta 3 and so forth, but you don't once you recognize that, you know, this angle is that angle, and then you can just apply n1 sine theta 1 that's equal to n4 sine theta 4. Okay, now regarding theta 5, let's look at this. So you have a theta 1 here at this interface, so we know that the angle reflection is theta 1 here. And then we're going to use, again, this is our normal at this interface, okay? And so this angle, theta 1, is actually this angle. So you can see that this is like angle of incidence, and then this is the, this is the angle refraction. So we can set up equations that n1 sine theta 1 that's equal to n(air) and then sine theta 5. Okay, so again, we are using the Snell's law. This angle is equal to this angle is equal to that angle. So this is angle of incidence, and this is your angle of refraction. So the angle is always in reference to the normal. So this is our reference line. So this is the angle, this is the angle. Okay, so your n1 is 1.3, and then your theta 1 is 40.1. So this is this, and that must be equal to n(air) times sine theta 5. So you have 1.3 sine 40.1, that's equal to m(air), which is 1, and then sine theta 5. So from there, you can calculate your theta 5. So you will get a numerical value that should be around 56.86 degrees. Okay, so this is how you tackle the problems like that, how you approach this problem. All right, so the next one I want to do is this one. Let me erase this. So we want to do problem 59. So this problem says that you have a light ray that is perpendicular to the face AB, okay, of a glass prism, which has the index of refraction of 1.52. You want to find the largest value for the angle so that the ray is totally reflected at face AC if the prism is immersed in air or in water. So let's do the scenario when it's in air, when the surrounding is air. So you have a light that's perpendicular incident on this on the surface. So you would expect that there's no deviation. The light will continue to go straight until it reach this interface. And then once it reaches this interface, let's draw the normal to indicate as our reference. So you can see that this is like the angle of incidence. And then your goal is to find at what angle of this angle that the refracted ray will be actually propagating along the interface, because it says total reflected, meaning that it is just about at this critical angle. This angle is actually the critical angle because light is actually propagating along this this surface. Okay, so in that case, you can see that this is the angle of incidence and this is the angle of refraction. So you will apply Snell's law. So you have to use the n glass and then sine theta c, and that's equal to n(air), and then times the sine of 90, because this is just the case when when total internal reflection occur. So this is your critical angle, and this angle refraction is actually 90 degrees. So then in that case, you have the 1.52 and then times sine theta c, and that's equal to n(air), which is 1, and then sine 90 is 1. So you can calculate your theta c. So in this case, you will calculate theta c that is equal to, let me see, hold on. You will calculate that to be 41.14 degrees. Okay, but that's not the final answer, because what we just did is that we calculate this angle, and the problem asks you to find the the largest value for the angle, you know, when of this angle, so that, you know, so this thing will propagate along the face. So you can see that this angle plus this angle is basically this angle. So these two angles add up to 90 degrees. So so for phi, if you want to calculate that, then you will use 90 minus 41.14. So the final answer for part A is that the angle is 48.86 degrees. Okay, so that's your part A. And so that's basically how you do this. Now for part B, so for part B, you will do exactly the same thing, except that because now instead of in air, it is now in water. So you still set up the equations like this. You still have the ng, the industrial fraction of the glass times sine of the critical angle that is equal to now is nw and then sine 90 degrees. Okay, so you still have the 1.52 times sine of theta c that's equal to the industrial fraction of water, which is 1.33. So instead of 1, I will use 1.33, and I still have my 1 sine of 90. So my theta c, after you do this, your theta c, you will get a value that is 61.04 degrees. Okay. And then following the same procedure, because critical angle is not the final answer, it is this angle. So you will use 90 minus 61.04. So when this whole thing is immerging water, then the this angle, what you found is that the angle has to be 28.95, so that the critical angle, actually the critical angle is when it's immerging water is 61.04, in such way that you know, this angle here is 28.95. Okay, so that's basically you know, this is how we demonstrate how to apply Snell's law you know, in various you know, scenario. Okay.